All right, let's try another example of an application of partial derivatives. Okay, example 6. A weight loss counselor has prepared a program of diet and exercise for a client. If the client sticks to the program, the weight loss can be expected in pounds per week. Okay, the weight loss that can be expected in pounds per week is given by, okay, the weight loss equals f of n comma c equals, okay, 1/8 n squared minus 1/5 c plus 1937 over 8, where c is the average daily caloric intake for the week, and n is the number of 40-minute aerobic workouts per week. Okay, so it makes sense that weight loss you can really determine fairly accurately just based on the number of workouts and average daily calorie intake. Okay, makes sense. So part A, how many pounds can the client expect to lose by eating an average of 1,200 calories per day and participating in 4 40-minute workouts in a week? Okay, and this whole function is all talking about what's happening per week. Okay, so we'll probably just want to answer the problems in like what's happening in pounds lost per week. Okay, so let's think about this one. I think for this one, all we're actually doing is just plugging in values. There's no derivative stuff going on here. So how many pounds can the client expect to lose if we plug in 1,200 for C and 4 for N, okay, because N represents the number of 40-minute workouts. Okay, so that 40 is not going to be used at all, so don't get thrown off by that extra number. The minutes of the workout is not part of this because we're just counting the number of those 40-minute workouts. Okay, so for part A, and again, interpreting is the hardest part about dealing with multivariable problems. Okay, so 40-minute workouts, we have 4 of them, and we have 1,200 calories. So all we want to do is F of N, so that's 4 workouts, comma, 1,200 calories. Okay, so 4 gets plugged in for the N, so we have 1/8 times 4 squared minus 1/5 times C, it's 1,200, plus 1937 over 8. Okay, and so calculator time, just typing this in, 1/8 times 16 minus 1/5 times 1,200 plus 1937 over 8. And so I got 4.125 pounds, and this is losing already built into the problem. So this is pounds lost per week. Okay, so the interpreting for that, not too bad because we're not doing the derivative parts yet. And we're not trying to like hold one of them constant or something like that. So we're definitely going to focus on our interpretations. Okay, so that one's just using our multivariable function and plugging in the values. Okay. So that's the expected weight loss per week with the 4 40-minute workouts and 1,200 calories per day. All right, part B, find and interpret the partial derivative of this function with respect to N. Okay, so the interpret part, again, that's the hardest part. So finding the partial derivative, not too bad. So let's just work this out. And just to give me some space, because again, I want my sentence to really be the main thing that we focus on. So the partial of f with respect to n, okay? So then we're just going to let n be the variable and c is the constant. So here we go, 1/8 n squared, so the power rule, the 2 would multiply down. So we would have 2 times 1/8 n, reduce the power by 1, okay? Minus 1/5 c, but that's all a constant right now. And then plus that 1937 over 8, that's also a constant. So this whole partial, we could write this as 2 times 1/8, that's going to be 1/4. So let's write that as n over 4. Okay, so that's the find part. Now let's move over to the interpret part. So let's go back and think about what does this function actually mean. So this function, the F function, is talking about the overall weight loss per week for N being the number of workouts and C being the average calories per day. So if we want to interpret what we just did, we found the rate of change of this weight loss function with respect to N. So what we can say is this represents the change in weight loss per week, okay, if you want, for each 1 unit change in the number of workouts. And so since the units are just one at a time, 1 unit change in the number of workouts. Okay, so I said the units are just one at a time. It's different than the power plants where some of the units could have been like in hundreds or something. Okay, so for each additional workout, we can expect that the amount of weight loss would change by that much. Okay, pretty much. Okay, and this is also, since we're doing partial with respect to N, if we're assuming that the calorie intake, okay, so let's also write that, if calorie okay, so that's probably a good sentence that sums it all up. That'll be the change in weight loss for each 1 unit change in the number of workouts. Okay, so you increase the workouts, then you get certain number of certain expected weight loss if we hold the calorie intake constant. Okay. The client currently averages 1,100 calories per day and does 3 40-minute workouts each week. What would be the approximate impact on weekly weight loss of adding a 4th workout per week? Okay, so this is a little bit tricky because we're currently at 3 and we want to go up to 4. Okay, so this is kind of the tricky thing, and this is why I really wanted to spell it out up here. Where was it? Right here. So if we do a change, a 1 unit increase, if we want to find out what is some kind of a rate of change in the overall function when the variable changes by 1, notice that the number that's plugged in there is the lower number. If we're changing from A to A plus 1, this number starts at A. So for our situation, if we want to change from N equals 3 to N equals 4, that's like the N equals 3 changing from 3 to 3 plus 1. So that means that we need the partial of F with respect to, and everything's changing based on our workouts, the partial of F with respect to N evaluated at, and like I said, we want it to change from 3 to 3 plus 1. Okay, so that's the tricky part there. We got to start with the 3, and since we're just adding that 1 extra one, this is going to do it that rate of change that we need. Okay, and then comma C, well, we're just doing 1,100 calories per day. That's just going to be a fixed amount of calories per day, so 1,100 in for C. Okay, so yeah, think about this as it's like N equals 3 to N equals 3 plus 1. So that's why we're putting a 3 in there for N in our partial derivative, because it's going to represent a 1 unit increase from 3 to 4, which is what our situation is calling for. Okay, kind of tricky, but now that we have that worked out, we already have that partial with respect to N worked out up here in part B. So N divided by 4, N is just going to be 3 divided by 4, and there's nowhere to plug in the calories, so that's fine. We're just done with that. And so that's it. What does this mean? Okay, so let's write this in a sentence. We can say, one more workout from 3 to 4 results in 3/4 pounds extra weight loss per week. Okay, and that 1100 calories pretty much didn't make any difference in this function here. All right, so the interpretation, always going to be the trickiest part when there's so many different variables involved. Okay, so I'll make a separate video to pick up on example 7.